So we've been looking at two proportions, and first we took the approach of simulating by shuffling those cards. Now let's look at what the theory says is going to happen. As you were playing around with the simulation app, you should have noticed that we're seeing that bell-shaped curve again, right? That distribution of possible proportion differences was being approximated nicely by our bell-shaped curve. And that's what the theory says. The theory says that under the right conditions, the distributions of all possible proportion differences will be normally distributed. And the middle of this distribution is going to be whatever the difference in proportions is in the population. Now, a lot of our tests are just to determine whether these two are equal or not. So the null hypothesis is that they are equal. So often this value for us is usually 0. We're hypothesizing that there is no difference, and then we're testing to see if there is. And as always, this normal distribution comes with some conditions. And if you recall, for a single proportion, the validity conditions were at least 10 successes and 10 failures. Well, now there's two populations, right? So we're going to have a proportion from one that consists of successes and failures, and a proportion the other consists of successes and failures. So all four of those have to be greater than or equal to 10. So the number of successes, these are our validity conditions. And number of failures in both populations, or in both samples, let's say. Number of successes and number of failures in both samples are at least 10. So again, like we've seen with the theory before, once you know that it is approximately normally distributed, then you can really, from the formula of the normal curve, get that p-value. You don't have to simulate. But the beauty of simulation is the simulation has no validity conditions. So you could always simulate, but you can't always use the theory-based approach. For example, if you recall from last time, we were doing the example with the cancer diagnoses in male and female. And so we had gender, male, female. And then we had cancer, no cancer. And our numbers were 4, 8, 13, and 16. And so for males, there's your success and failure. For females, there's your success and failure. So these validity conditions are really saying that all four of those entries in the table need to be at least 10. Unfortunately, we're a little small on the sample size or on the amount of successes here in both. And if you go back to the video where we were simulating, that normal curve was not quite matching what we were seeing in the simulation. And that's because it wasn't quite normal enough. So the previous example would not work under the theory-based approach. So let's imagine a situation where we had slightly larger samples. So say we had some new data, male, female, cancer, no cancer. And what I did is I just made these larger but the same proportions. So 12, 16, 39, and 32. So let's go over to the theory-based applet, and we'll see how we can use it to do our statistics on these two samples here. OK, so I'm in the theory-based applet. Remember, this works for both 1 proportion, 1 mean, 2 proportions, 2 means. So we're looking at 2 proportions. And you can use data, but we've just got summary information here. Group 1 is going to be our males. We had a total of 41 males. And there was 12 cancer diagnoses. And we had a total of 48 females and 16. And notice it automatically populated what those p-hats were for the two. And we get our, when we hit calculate, we get our nice segmented bar graphs here. One nice thing in the theory is if you prefer to think of it one way or the other, you can flip the either p1 minus p2 hat or p2 hat minus p1. All that's doing is really flipping it around the other direction. But you should keep in mind which way you're doing it. So I'm going to keep it as p1 hat minus p2 hat, because that's how we were doing it previously. And then so remember, by default, these are not checked. So I'll turn on the test of significance. And we're wanting to know is this proportion really different? Is the rate of cancer in the population really different from 0? So is it equal amongst males and females, or is it different? So our alternative hypothesis is that in the population, there is no difference. And we'll do our calculation. And notice it automatically put in the standard statistic here for us and calculated this p-value of 0.6806. Very large p-value, right? This would not at all be unusual to see if there was actually no difference, right? Remember what a null distribution shows. These are the things you would expect to see if there really was no difference in the population. And we are not that far away from the middle with our negative 0.041. And so this is not strong evidence at all. We would conclude that we do not have enough evidence here to say that there's a difference in cancer rates among males versus females. Now, one thing we did not do in simulation, because it would be a bit more involved, is look at confidence intervals. So in the theory, off that same distribution, we could have it calculate a 95% confidence interval, or 90 if we wanted. We could change that. But we've typically been doing 95, so we'll keep it at 95. And so one thing to notice about this confidence interval is that it straddles 0, right? It runs from a negative 0.23 roughly to a positive 0.15. And so we can see just from this confidence interval that we are not going to be confident saying that the difference is not 0, because 0 is in there, right? Whenever you have a confidence interval for differences that runs from a negative to a positive, you are not going to be confident in saying that the difference is either positive or negative, because it contains a little bit of both. So this large p-value, notice, is giving us something that's not very conclusive here in the confidence interval, because this thing tells us the difference in cancer rates could be in favor of males or in favor of females, because it has both. So let's kind of tweak our data to see, let's get something really significant. So let's make these greatly different. So let's say that instead of sampling 48 females, there had been 120 in there. Now look at our p-value. We have a pretty large difference here, about a 16% difference in the rate of cancer now between males and females. The female rate is very small now at 13%. We're still up at 29% for the males. So what would you expect? Well, here's what you would expect to see if there was no difference. And we're landing way out here at negative 15%, negative 16%. Actually positive, sorry, we're over here. But with our two-tailed test, we're getting a p-value of 2%, so pretty significant. And now notice our confidence interval. Our confidence interval is entirely positive. So whatever the difference is, we're 95% certain it's a positive difference. So we're 95% certain that males would have cancer at a rate somewhere slightly more than 0% up to 31% on our 95% confidence interval. So this is really a tip-off too that you've got something significant. When these numbers are entirely positive or entirely negative, you are clearly on one side of 0 or the other. So these two kind of tell the same story here. This very small p-value means we've got something significant here in our sample. And so is this confidence interval. So we can make that determination from either one. They're kind of flip sides of the same coin.